In the next example, we're going to determine the non-permissible values for cotan theta secant theta over cosecant theta, and then we'll simplify the expression. Remember, non-permissible values in this unit refers to divisions by 0, so we can't allow any denominators to be equal to 0. In our main expression, this means that cosecant theta would not be allowed to be equal to 0. But if we check a graph for this, we'll actually find that cosecant theta, which we'll represent using 1 over sine x, never equals 0. We know this because on the graph it never crosses the x-axis. This just means that secant theta cannot be 0, and therefore makes no non-permissible values within the context of the largest fraction there, the cotan theta secant theta over cosecant theta. However, that doesn't mean that cotan theta, secant theta, and cosecant theta couldn't have non-permissible values of their own. This will become obvious once we rewrite them in terms of sine and cos. If we look at the cosecant theta graph, we do notice that there are some non-permissible values represented by vertical asymptotes. Now our graph doesn't actually show these, but let me add them for you. Those dotted vertical lines represent values that cosecant theta is not equal to. That suggests a division by 0 was happening. Now, we can see in this case that they're happening at negative pi, 0, pi, and 2 pi, because that's where sine theta is equal to 0. This will make more sense when we look at this algebraically. If you were to graph the original expression of cotan theta secant theta over cosecant theta using 1 over tan times 1 over cos divided by 1 over sine, you would see this flat line. This suggests that when we simplify the expression later, it will be equal to a constant value, in this case 1. But if we use our trace function, we would actually be able to find some points of discontinuity that don't actually appear. This isn't how you are going to determine your non-permissible values, but since we were already looking at the graph of cosecant theta, I thought it would be worthwhile to explore this. Let's use our algebraic method to be a bit more efficient here. We'll replace cotan theta with cos over sine theta. We'll replace secant theta with 1 over cos theta. And we'll replace cosecant theta with 1 over sine theta. This means we have denominators of sine theta. And we know that sine theta is 0 where the y-coordinate is 0 on the unit circle. This happens at 0, pi, 2 pi, and every multiple of pi. We also have a denominator of cosine theta. Cosine theta is 0 where the x-coordinate is 0 on the unit circle. This happens at 1/2 of pi, 3/2 of pi, and every addition of pi after that. When we consider these two cases together, we see that at 0, 1/2 of pi, pi, 3/2 of pi, 2 pi, basically every quarter rotation we have a restriction, a non-permissible value. So we will say that x cannot be every multiple of pi over 2. We note here that n represents an integer number because it must be a whole number, either positive or negative. Now, we've already written our first step in simplifying the expression because we wrote our ratios in terms of sine and cos. In our numerator, we see that the cosines will cancel out, and we're left with 1 over sine theta equals 1 over sine theta. Given that both the numerator and denominator of this complex fraction are equivalent, we can reduce this expression down to 1.